Good afternoon. In this opportunity, I'm going to talk about a study of transient angle stability in microgrids with synchronous generation through a comparative analysis of operating scenarios. My name is Ivan Pazmiño Ordóñez, and this work has been done in cooperation with Edwin Ponce Minaya and Hugo Pico Mera. In the next minutes, we are going to talk about the abstract, introduction, system description, methodology, system modeling, results, and conclusions related with this paper. First, abstract. Improving the understanding of the dynamic response of electrical power system to disturbances is a topic of high interest both for the academic community and for network operators who must take measures to guarantee the stability of the system. So, the following presentation proposes a comparative study of operating scenarios through the implementation of a simulation tool to study the transient stability of microgrids with synchronous generation connected to the electrical power system. MATLAB Simulink has been used for its development. From this computational tool, the simulation of the dynamic response of a typical microgrid with synchronous generation is carried out in order to evaluate its angular stability against a fault condition in different stages. Introduction. Microgrids are small-scale power electrical systems with distributed energy generation resources, such as microturbines, synchronous fault generators, wind generators, or photovoltaic panels, in conjunction with energy storage devices. One of the main advantages of the microgrids is that they present flexibility in their modes of operation. For example, the systems can be operated autonomously or linked to the conventional electrical network. In this picture, it can be seen the microgrids operation modes. One of them is the island mode, and the other one is connected to the network. Referring to the island mode, we can find two different options. One of them is operating with the energy storage system, and the other one is without energy storage systems. However, in the present paper, the study is focused in the mode when it's connected to the network, where they are relatively stable. System description. For the study addressed in this document, a characteristic system of a microgrid with synchronous generation connected to an infinity bus through a transformer and a double transmission line will be used, as it can be seen in the present picture. Methodology. To evaluate each one of the operating scenarios, it has been implemented a MATLAB Simulink simulation tool based on the mathematical foundation of the criterion of equal areas. So, in order to evaluate the behavior of delta angle and the related variables of interest, the analysis is focused in the critical clearance time of the tested failure, which is evaluated and compared in each of the scenarios of analysis. The simulation reproduces the response that a microgrid with synchronous generation would have in the event of a three-phase fault. In order to quantitatively evaluate the impact that each one of the operating scenarios represent on the system, the values of inertia constant h and the maximum power before and after the failure are modified. This analysis is carried out in 4 operational scenarios as indicated below. The first is a base case with values of tension in the generator equal to 1 per unit, tension in the infinity bar equal to 1 per unit, equivalent reactance equal to 0.5, an initial angle delta equal to 18 degrees, a constant of inertia h equal to 10 seconds, and a coefficient of variation of demand with frequency equal to 0.02. In case 2, taking as reference the data provided in the base case, the value of h is increased by 20%. In case 3, the base case is modified by increasing the maximum power during the failure, so that only drops to 20% of the maximum power before the failure. Finally, in case 4, the base case is modified by increasing the maximum power by 20% before the failure. In each one of the analyzed scenarios, the corresponding critical fault clearance time is analytically established, which is corroborated by the dynamic response of the system after entering it in the simulation tool. The frequency used for the study has been the one available in the most regions of America, that is 60 Hz. System modeling. Since the frequency stability of the system will be evaluated, the representation given by the oscillation equation is used. It needs to be mentioned that for this case of analysis, a function of magnitudes in values per unit is used. It can be seen in the present picture, where h is the equivalent of inertia constant of the system, and d is the coefficient of variation of the demand with frequency. Results. When we compare the behavior of two of the main variables of interest, which are the angular velocity and delta angle, it can be seen that when the fault clearance time is under the critical, as shown in the figure in the top, the system recovers its stability. Conversely, when the fault clearance time is over the critical, the system becomes unstable and it doesn't recover. So, analyzing each of the cases studied above, it can be seen that in the first case, the critical clearance time was calculated equal to 495 milliseconds. In the second, its h value was increased by 20% and the critical time increased from 496 milliseconds to 543 milliseconds, which represents approximately 9%. It means that by increasing the inertia constant in the system, it improves its ability to recover from failure. In case 3, the base case was modified by increasing the maximum active power during the failure. So, it only dropped to 20% of the maximum power before the failure. Here, the critical time was increased from 543 milliseconds to 720 milliseconds. So, it has increased by 32.5%, which is even greater than the one obtained in case 2 as a result of increasing h. In case 4, the base case was modified by increasing the maximum power by 20% before the failure. Again, there was a positive impact on the response of the system to the failure. That is, the critical time of 496 milliseconds has been increased to 505 milliseconds. Conclusions. Referring to the factors that significantly affect the transient stability of synchronous generator, it can be concluded that regarding the fault clearance time, the shorter the clearance time, the greater the stability is. Regarding the selectivity of the protections, the higher it is, the greater the power after the failure and more stable the case is. Regarding the inertia of the generator, the higher it is, the less the machine accelerates and the more stable the case is. Regarding the voltage of the transmission network and the internal voltage of the generator, the higher they are, the greater the power after the failure and the more stable the case is. Please, if you need further information about this topic, don't hesitate to contact me to this email. Thank you very much.